continue on with chapter 4. So your chapter 4 exam is going to be on Monday. So what my plan is today we're going to finish up most of the stuff from chapter 4. And then today I will go ahead and post the answer keys for chapter 4. So that would just be this week. This week's 3 answer keys I'll post on the SI website. And let me put the link for that in the chat again, in case you don't know where the SI website is. Here we go. So in the chat, there's the SI website. So sometime this evening after the session, I will post the answer keys so that you can use those to study. Now Monday, people had mentioned that Monday it would be nice to have a review. So I think Monday, unless there's any objections, we will review chapter 4. So if you have any questions you want to bring on Monday, general chemistry questions or regarding this chapter, feel free to bring those on Monday and we can discuss those. What questions do you have before we get started today? Okay, well, let's go ahead and get started. I want to apologize in advance for all the noise you're going to hear in the background. The roofers are still here today, so you're going to hear a lot of banging and stuff. All right, so today we're going to speak about oxidation numbers, oxidation reduction reactions, and then maybe some stoichiometry reactions that are occurring within a solution. So let's begin by discussing a little bit about what are, let me close this. What are oxidation numbers and why do we use them? So does anyone know or have or want to share why they think we study oxidation and reduction reactions? So here's what I would say. So why are we going to study oxidation reduction? So this is primarily to analyze the transfer of electrons. So almost everything we're going to be doing today is regarding oxidation reduction, and that just means it's a reaction where you're having some sort of a transfer of electrons from one element to another. Now, why do we care? Well, there's lots of applications where you would use this. For one, batteries is one. You're just running some sort of oxidation reduction reaction, and you can generate a electrical potential from those reactions. It's also related to light emission. So something like fireworks are oxidation reduction reactions. So we need to know what's going on with the electrons in these reactions to be able to tell, know what we can use them for. So here are some rules for oxidation numbers. Now, maybe you have read the notes already and maybe have heard about oxidation numbers. Now, oxidation numbers are sort of like charges. Remember last couple chapters we were talking about charges from the periodic table? Oxidation numbers are very analogous to those. Now, there's a few rules for determining the oxidation number, and we determine the oxidation number for each atom in each compound. So here's the rules. Pure elements have an oxidation number of 0. So anything that is on its own, like O2 or N2, anything like that, always has an oxidation number of 0. Next step is, can you break the compound down into polyatomic ions? So let's look like this one right here, K2SO4. We could split this into potassium and sulfate. They're 2 separate compounds that we can break them into. Next, hydrogen is always going to be +1, and oxygen is always going to be -2. The exceptions to that would be if you have a peroxide, which would be hydrogen peroxide is 1, H2O2, or another one is OF2, in which case what we'll discuss in problem number 1, oxygen is not -2, but most of the time oxygen is going to be -2. And lastly, if all else fails, are there elements whose oxidation number you can find from the periodic table? So that would be something like the first column on the table is a +1, for example. So let's do some examples with these and find oxidation numbers and put these guidelines to use. Before we do that, what questions do you have on the general rules for oxidation numbers?
So when you said pure element O2, but then O is always -2, what's the difference between them? You're on mute.
Thank you, Kristen. So this is like a hierarchy of rules. So the ones that are at the top of this list up here take priority. So if oxygen is usually -2, but above that in this hierarchy is pure elements. So if oxygen is by itself, then it's 0. And then we move down this hierarchy of chain. Now, if it's in a compound, that's when it's -2. Does that make sense a little bit?
Yeah, it does. Thank you.
Okay. Yeah, great question. So let's work on a few here, and then I will let you have some time to go at it yourself. Now F2, so what we're going to do is find for each fluorine, I'm going to say F equals, and for here I'm going to put the oxidation number. Now fluorine is all on its own here, so what should the oxidation number be for fluorine?
0.
Yes, very good. So I'm going to say F equals 0, so that means the oxidation number for each fluorine is 0. That's because rule number 1 up here, pure elements have an oxidation number of 0. All right, next one, we have phosphorus and we have oxygen. So let's look at our rules, and we're going down from the top. Okay, pure elements, no polyatomic ions, no hydrogen. Well, the next rule is oxygen is -2. So oxygen, we're going to say equals -2. Now we don't do 4 times -2 for the total. We just do each oxygen is -2. Now, how could we find the total for this phosphorus? Well, here what we're going to do is we're going to realize that the total for this polyatomic ion is -3. So the total charge of this is going to be equal to -3. So what I'm going to do is do kind of like an equation. We have 1 phosphorus, we have 4 oxygens, and each of the oxygens we said was -2. So we have 1 phosphorus up here, 4 oxygens, and each is -2. And the overall charge of this molecule has to equal -3, because -3 is the charge on this molecule. So here we're going to have, P -8 equals -3. And hopefully I can move this down. There we go. So the P is just representing the oxidation number on phosphorus. And then from here, we want to add 8 to the other side, so we get +5. So that means the oxidation number on the phosphorus is +5. I'll box all the answers to be a little more explicit. So for these cases, we have to use like a little mini equation to find the charge. Let's do one more, and then I'll let you guys try to do these next 3. So we have H2O2, so we have H and O. So let's look at our hierarchy of rules up here. So coming down here, we get to hydrogen. So hydrogen is always +1. So we're going to write that down. And this takes precedence over the oxygen because, again, these rules are like a hierarchy here. The hydrogen is above the oxygen in these rules. So we have hydrogen and oxygen. Now, again, we're going to have to do, you can just think about this and find the oxygen if you want, but I like to do an equation. So we have 2 times hydrogens, and each hydrogens are +1.
Fuck!
And each oxygen, so we have 2 oxygens. So 2 times oxygens, and this is going to be equal to the total charge of the molecule. Now, what is the total charge of this molecule, H2O2? What is this equal to here?
0.
Okay, so Sarah said 0. Why? Why is it equal to 0? You're right. Do you know why you're right, Sarah?
Because there's no like number at the.
Okay, yeah. So anytime there's not a number up here, that means it's equal to 0, or the total charge is equal to 0. I'm going to put a 0 here.
Can we laugh about what just happened?
Yeah, what? Yeah.
I am so sorry. That was an accident. I did not mean to say that.
That's okay. It's everyone has their mic unmuted sometimes. Happens to everyone. It's all right. Okay, so we have 2 plus 2 oxygens equals 0. So that means that each oxygen is equal to -1. So this might be kind of like a long-winded equation just to get the answer of oxygen equals -1. Another way you can think about it is to just say, well, look, we have the same number of oxygens, same number of hydrogens. So if hydrogen is +1, then the oxygen has to be equal and opposite, so -1. What questions do you have on these 3 examples?
So is the reason that the site like the PO4 one is the
Yep.
reason that they're not like equal in plus to minus because there's more oxygen than there is phosphorus?
Yes, that's exactly right, Ben. And there's a charge on that molecule, which was -3. So both of those together. Yeah.
All right.
Okay, so why don't you guys, sorry again for the noise. The guys are like right outside my window. Try to work on these next 3 for a few minutes, and then we'll come back together.
I have a question. It doesn't necessarily have to do with like these examples,
Yep.
but do you ever like use the coefficient when you're trying to determine the oxidation number, like ever multiply it by like the number, or does the coefficient have nothing to do with it?
Great question, Laura. So the coefficient has nothing to do with it. And the reason is because we're trying to find the charge for each individual element. So if there was like, if you had like a 2 in front of here, that would be completely irrelevant to the problem.
Okay.
Was that answer your question?
Yes, thank you.
Okay. Okay, we can work on these ones together. If you're still working on your own, that's completely fine. Again, I'm sorry for the noise. These guys, you can't see, it's like, but they are like less than 2 feet from me right outside my window. So let's work on K2SO4. Now, one of the things you can do is break these down into polyatomic ions. So we have a K2 and an SO4. Now, what are the charges on both of these? Well, we know that SO4 has a charge of -2 because that is one of the polyatomic ions we've been working with this semester. So this side is -2, therefore the left side has to be equal and opposite, or +2. So let's write down the 2 or 3 elements we have here: potassium, oxygen, and sulfur. Okay, so potassium, we have 2 potassiums on the left, and they share a charge of +2. Therefore, each potassium would have +1. So just 2 divided by 2. Another thing you could do is look at the periodic table. So let's run over there quick. Periodic table. Where is potassium? Okay. Potassium is right here. This is in column 1. Therefore, all elements in column 1 have an oxidation number of +1. So there's 2 ways to get the potassium on this one. What about oxygen? Well, we know oxygen, if it's in a compound, it's -2. And then sulfur. So for here, we're going to have to do the same thing with our equation. So we have 1 sulfur plus 4 oxygens, and each oxygen has a charge of -2. And this equals a total charge for SO4 equals to -2. That's this number right here. So from here, you can get, so sulfur is equal to +6. So sulfur equals +6. All right, moving on. So COCl2. So we have oxygen, chlorine, and carbon. Okay, so we have oxygen. Again, oxygen is -2. Chlorine, we can go to the periodic table for chlorine. So let's run over to the periodic table. And chlorine is on the right side over here. So that would be equal to -1. It's in the -1 column. Now the question might arise, why did I do chlorine, not carbon? If I could look in the periodic table. So I guess a general rule of thumb that I would give you is you should start from the columns that are on the outside of the periodic table and move your way in. So here's what I mean by that. You should start at column 1 and work your way in this way, and start at column -1 and work your way in this way. So if we were coming across the periodic table this way, we would run into chlorine first before we got to carbon. Again, I'm not sure if this is a technical explanation, but this is how, I guess, a practical way to go about it. So as we're coming left, we run into chlorine first, then carbon. So chlorine is -1 from the periodic table. So to get carbon, we have to do the equation again. So we have carbon plus oxygen, which is -2, plus 2 chlorines, which is each -1. And this equals a total charge of 0. Therefore, the carbon is going to be equal to +4. So carbon here is +4.
Did you get the +2?
Oh, good question. So 2 just represents that there are 2 chlorines right here. So we have chlorine, or we have carbon. This here represents the oxygen. So this one is the oxygen. And then this piece here is the chlorine. I put the 2 there because there's 2 chlorines, and each of them has a -1 charge. Did I answer your question, Ben? Okay. All right, let's do the last one, H4P2O7, PO. Okay, so let's run down our hierarchy. So hydrogen is +1, Oxygen is -2. And then the last one we get from our equation. So we have 4 hydrogens, each with a +1 charge, plus 1 phosphorus. Oh no, 2 phosphoruses, isn't it? So 2 times P plus 7 oxygens, each with a -2. And this is going to equal 0. So solving for this, this is a +1 here. That's a little confusing. +1. So phosphorus here will be +5. So those would be the oxidation numbers for all these compounds. What questions do you have on finding oxidation numbers?
So why is it sometimes like we can just look at the periodic table and write down a number, and then why is it sometimes we have to like solve for it, like the K2SO4?
Good question, Kristen. I couldn't give you a technical reason, but for me, the reasoning falls in the order of this hierarchy that I've made. So the reason I put the rules in this order is because you should do everything else you can possibly do and then use the periodic table as a last resort. So you see here, if there are pure elements, if it's hydrogen or if it's oxygen, in this case here, we were able to use just those rules. We didn't need the periodic table. Where if any of these first top 4 rules don't satisfy, then we go to the periodic table. Again, I don't know if I could give you a technical answer, but it's just sort of a hierarchical order of steps that you should use. Does that help at all, Kristen?
Kind of. So if we know H and O, then
Yep.
we're doing the equation to solve for like the other element?
Correct, exactly.
Okay.
Yep.
Is oxygen like always going to have a -2 charge?
Great question. So the question was, is oxygen always going to have a -2? Almost always. Now, I intentionally put one of these examples here is one where it isn't -2, and that was the hydrogen peroxide right here. In this case, it was -1. Now, the only case when it won't be -2 is if hydrogen is the only other one, or hydrogen or fluorine is the only other compounds. In that case, the hydrogen takes the importance over the oxygen, and you have to solve for the charge on the oxygen, which is just what we did here. So I think the only 2 they would throw at you, and I'm not sure if that was Ryan who asked that, but are H2O2, which is the one we did, and then OF2. So why don't we do this one real quick? And in this one, in this case, this is an exception where fluorine is -1 and oxygen is +2. So if I were you, I would take these 2 examples right here and just write them down somewhere. If they're going to try to trick you with one of these, it's probably going to be one of these 2 compounds. And I guess that would be the guidance I would give to you guys. Did that help maybe a little bit?
Yeah, that made sense. Thanks.
Okay. So let's move on and do some actual equations with these. So you might not be asked exactly what we were doing up here, but you could be asked something like problem number 2. So problem number 2 says, which elements are oxidized and which are reduced in the following equations? And further, what are the oxidizing and reducing agents? Now, what this question is asking is, we have some sort of a chemical reaction, and this is having electrons are exchanging from one atom to another. It wants to know which are doing the exchanging and which is taking electrons and which is receiving. So I'm going to put down a acronym here that you guys may have seen in the class notes. And the acronym is oil rig. Does anyone know what oil rig means?
Is it just like oxidation is losing and reduction is gaining?
Very good, yes. So Sarah said oxidation is loss of electrons, and then reduction is gain of electrons. So that's where we get the OIL, oxidation is loss, and rig, reduction is gain. So to figure out which are oxidized and which are reduced, we need to find what are the oxidation numbers. So let's do A together, and then I will let you have an opportunity to try B on your own. Now, I like to write down under the arrow each of the elements on both sides, almost like we were balancing, but rather than balancing, we're finding the oxidation numbers. So on the left here, we have chlorine, and it is by itself. Therefore, what is the oxidation number of chlorine?
Is it 0?
Yes, it is, Laura. It is 0. And why is it 0?
Because it's just like an element by itself.
Yes, that's exactly correct. And that's all. That's the answer if you're ever asked. Any element that's by itself is 0. So chlorine, we say, is 0. Moving on to sodium and iodine. Well, there's no rules we can use for these, so we just have to rely on the periodic table. So let's go over to the periodic table, sodium and iodine. So we have sodium here. This is in the +1 column. So sodium is +1. And iodine is down over here. This is in the -1 column. And so they should always be equal and opposite to one another. And in this case is no exception. So we have 0, +1, and -1. Now on the right side, now we have iodine by itself. That means that iodine on the right has a charge of 0. And then in this here, we have sodium again and chlorine. So they are in compounds. So again, we look at the periodic table and we find that sodium is +1 and chlorine is -1. Notice that these charges or these oxidation numbers are completely irrelevant from the coefficient on this front here. We had a 2 right here, but that did not change the oxidation numbers at all. So just something to note. Now that we have the oxidation numbers, which one is losing electrons and which is gaining? Does anyone have an opinion on that?
Chlorine is gaining and iodine is losing.
Yes, that's exactly correct. So we have chlorine is going from 0 to -1. That is a gain of electrons. This is completely backwards. So chlorine gains electrons. So the E- just means electrons. And iodine loses electrons. So just be careful. This is backwards because chlorine is going more negative. But because an electron has a minus charge, getting more negative actually means you're gaining electrons. And iodine, on the other hand, is getting more positive. Therefore, it's losing electrons.
Couldn't you
It's
just
like,
ignore the charges when you do that then?
say that again, Ben.
Couldn't you just ignore the charges if you were thinking about it that way then?
Explain what you mean.
So like if you're going from 0 to 1, that's gaining, whether it's a negative charge or not. Like obviously, like if you pretended that the negative wasn't there,
Yep.
it would be gaining 1, which it is already. And if you pretended the negative wasn't there for the iodine, it'd be losing 1 because it's going to 0.
That probably works out in this case. If you, what you're essentially doing is just flipping the sign on it. And if that makes sense in your mind, Ben, you could definitely go about it that way. I don't know who came up with this naming convention where an electron is a negative, but we're stuck with it. So chlorine gains electrons. That means chlorine is reduced. And then iodine, on the other hand, iodine loses electrons, iodine is oxidized. So that's what you would write for the answer. Now, there's also another thing called the agents. Now, the agents are what is doing the reducing or is doing the oxidizing. And these are just always the opposites. So if chlorine is reduced, that means it is the oxidizing agent. And if iodine is oxidized, that means it is the reducing agent. What questions do you have on number 2, part A?
Just to clarify, is
Yep.
it supposed to be flipped like that? Chlorine is reduced, meaning it's oxidizing.
So it's oxidizing agent. So yes, they are flipped. So if something is reduced, that means it is the oxidizing agent or the thing that is oxidizing the other one. So I know it's kind of weird that they're flipped, but so then iodine is oxidized, therefore it would be the reducing agent. Does that make sense?
Yeah.
Okay. So why don't you take some time and try to work through part B. So again, just start out by writing all of the elements under the arrow and then find the oxidation numbers.
My internet cut out. Why did we say Cl was an oxidizing agent, and why did we say I was a reducing agent?
Okay, so let me explain again. Were you here, Kristen, for this part where we talked about oil rig?
Yes.
Okay, so we determined that chlorine gains electrons and iodine loses electrons. Did you follow up until this part?
Yeah, I did.
Okay. Now, once we determine which one gains and which loses electrons, this is where we use the oil rig. So we say, which one gains? Well, reduction is gain. Therefore, we say chlorine is reduced because it gained electrons. And oppositely, we have iodine loses electrons, and that would be oxidation is loss. So we say iodine is oxidized.
And the reactant part, the second part, the H2O2 in the second one, since it
Yes.
only H with oxygen, is it +1, -1?
Yes, it is. Very good. Kristen, did you follow up until what I was saying?
Yep.
Okay. And then I'm not sure if you caught the agents. So the agents are like what is doing the reducing, what is doing the oxidizing. And those are just you flip the name. So for example, if chlorine is reduced, that means it is the oxidizing agent. And if iodine is oxidizing, that means it is the reducing agent.
Okay.
Does that make sense?
Yep.
Okay,
Thank you.
you're welcome.
What do we do with SO4 since it's only on the right?
So you are just gonna have to break it up like we did up in these ones. And then just break it down into each individual element. Did that help, Ben? Or okay. Okay, let's try to do part B together. So first part, we have PB and S. Now there's no rules for these. That means we have to look at the periodic table. So let's go over there quick. So where is PB and where is S? So PB is, look at me, I can't even, there it is. So PB and sulfur. So which one do we get first? Which number from the periodic table? Well, again, the general rule is just to start coming in this way. And which one do you get to first? Well, we get to column -2 first, so that is sulfur. So we're going to go over here and say sulfur equals -2. So sulfur is -2. Now, if sulfur is -2, lead has to be equal and opposite to that. So +2 for lead. Now moving on to H2O2, this one here. So we have hydrogen is equal to +1. And this is the same example we did earlier, which is one of the only cases where oxygen is not -2. And this one, like we saw earlier, it was -1. So you can just think about this. If there's 2 hydrogens and 2 oxygens, then they have to be equal and opposite to whatever number they are. So hydrogen's +1, oxygen is -1. And on the right side, we have lead sulfate. So this one here, we're going to break up into polyatomic ion. So we know SO4 is -2. Again, that is one of the polyatomic ions. And let me flip over to the polyatomic ion chart real quick. If you don't remember what these are, I'd recommend you take a photo. And just a brief refresher for everyone, the polyatomic ions are just a list of compounds that are so common that we just give them their own name. So we have SO4 is one of those, that is sulfate, and it has a charge of -2. That is where I got here that sulfate is -2. So if sulfate's -2, lead has to be +2. So then we're going to have to come here. We know oxygen is going to be -2, like it almost always is. And we can solve for the sulfur. So sulfur, using the equation. So we have 4 oxygens, each with a -2. And this equals an overall charge for sulfate of -2. So solving for that, we get sulfur is equal to
Could you go
plus.
through that one more time?
Yep. Yeah, let me go through this one more time. So we have SO4 and PB, and we're going to break this into the metal and the polyatomic ion. Now sulfate, from our polyatomic ions table, we know it is -2. In other words, this equals sign here will be -2. This is where I get the equals -2. Now, what is on the left here? Well, we know the charge of oxygen, and each oxygen is going to be -2 because that was one of our rules we went over. But we don't know the charge of sulfur. So here's the -2 for the oxygens, and there are 4 oxygens in this compound. So SO4, 4 oxygens. So we want to solve for sulfur. So let me maybe expand on this just a little bit. So we have S, and then 4 times -2 would be -8. It equals -2. So solving for S, that's going to be equal to +6. All right. So put +6 here. And now the last one here, H2O2, or H2O. So hydrogen, we know is +1. Therefore, oxygen is equal to -2. So +1 here, and the -2 fits in perfectly. And if you're wondering, what if the oxygen in the water is a different charge than the oxygen here? I'll just tell you right now, they're never going to give you a problem where the oxygens are different charges on the same side. They should always come out to be the same. All right. What questions do you have on finding the oxidation numbers before we get to the reducing and oxidizing?
When I look at my periodic table, is PB +4 or is it +2?
So lead can be different in different cases. So if you look at the periodic table, yes, it is in the +4 column. So PB is right here. It's in the +4. But because sulfur is closer to the end of the periodic table, that takes precedence over the lead. And again, I can't give you a technical explanation other than you should locate the two, sulfur and lead, and then move in from the right. And because we hit sulfur before we hit lead, then we use the sulfur charge. Did that make any sense?
Okay.
Yeah, I'm sorry. It's a little confusing, Kristen. We'll continue to do a couple examples, and maybe it will come slowly. I know oxidation numbers were always hard for me to learn, and there's so many rules floating around.
Okay.
So let's figure out which is oxidized and which is reduced. So I'm going to use green for this.
I have one last question.
Yep, go ahead.
So in H2O, because it's only hydrogen and oxygen, how come it's not +1 -1? It's -2 and +1.
So the reason is because there's a different number of oxygens than hydrogens.
Okay.
If we did the equation, we'd have 2 times +1 plus oxygen equals 0. So this would be 2 plus oxygen equals 0, or oxygen equals -2. Does that help at all, Ben, or still a little confusing?
I'm just gonna roll it since they don't have the same like bottom number that.
Yeah.
Okay.
Yeah, I know. Again, the stuff is really confusing. The only way it ever came to me was just by doing a lot of practice problems. So, all right, let's see here what's going on. We have sulfur going from minus to plus, -2 to +6. That would be losing electrons. So it is getting more positive, so it's losing. What about oxygen? We have oxygen is gaining electrons. It is getting more negative. Therefore, it is gaining electrons. So what does this mean? Well, this means that sulfur losing electrons is oxidation. So we say sulfur is oxidized. And for oxygen, oxygen is gaining electrons. So that means oxygen is reduced. Now, if we were asked to find the agents, so again, these are just going to be the opposite. So if something is oxidized, that would mean it is the reducing agent. And if something is reduced, that means it is the oxidizing agent. What questions do you have on the oxidation and reduction reactions? Okay, so we don't really have time to start another problem, but let me just do a quick survey of what I had here. I had a problem with stoichiometry and solution. So we'll try to hit this on Monday for a review. And then I also had some on oxidation half reactions. So you may have seen that name floating around, and we'll try to do an example of those on Monday as well. So for Monday's review, feel free to bring any chemistry questions or send me a message letting me know if there's a specific topic you want to for us to hit on Monday. Okay, well, let's stop here. Feel free to hang out for a few minutes if you have any questions, and I can answer those for you. Otherwise, have a great weekend, and I'll see you on Monday.
Okay, so I kind of came to this SI because we got through the first half of the chem assignment.
Yep.
The one I really need is, I think it was number 4. Is there any way you could do that?
For the activity series or the half reactions?
Well,
All the above.
Yeah.
Okay, why don't we do one example, and then that could at least get you going.
Thank you.
So there's this thing called the activity series. Now the activity series just predicts what the products would be in a reaction. Now this is available on your notes. I think it's the very bottom of your notes, or this is available on the SI website. Now what this says is what is your metal here? And then this is the reaction, the oxidation reaction it would undergo. And I know it's kind of low quality, but this is lithium plus and electron. So if lithium was oxidized, the reaction would be lithium solid goes to lithium aqueous plus 1 plus an electron. Let's do another one for calcium. So this would be calcium solid turns into calcium 2 plus aqueous plus 2 electrons. So what's happening is those 2 electrons are coming off the calcium and then becoming separate. Now, the other thing to note is that there's a hierarchy that determines will a reaction happen, and that is up like this. So, and the rule is a reaction. Let me just make sure I say this right. A reaction will happen if it is higher on the activity series than the other metal. The heck do I mean by that? Well, let's do an example. So let me circle the 2 that we're interested in for our problem. So we have iron 2 plus and potassium solid that are being put together. The question is, will a reaction happen? And this is what we use the activity series for. So how we do this, we take the one that is solid. This one is solid, and this one is aqueous. So take the solid and go to the activity series. So we have iron and potassium. Let's look on here. We have iron right here and potassium. So let me write down the rule here, maybe up. If the solid is higher on activity series then aqueous. I'll move this in just a sec. Then reaction will occur. Oops, sorry. Put it right here. So if a solid is higher on the activity series than the aqueous one, then a reaction will occur. So remember, in our problem, we had potassium was a solid and iron was aqueous. Therefore, the potassium is higher on this list, therefore a reaction happens. So we say yes, reaction. And the question is, what would the products be in this reaction? And the way you do that is you look at the activity series. So let's look here, see what potassium goes to. So potassium goes from potassium to K plus. So let's go back here. This is going to be K plus aqueous plus iron. Now iron is going to be running this reaction backwards. So let's look over here. Iron is at 2 plus aqueous, and it's going to go to solid. So this is, we're running this one backwards. So this reaction runs forwards, and the other one runs backwards. They're just going opposite.
So is it always the aqueous that runs backwards?
Yes. So the aqueous one is going to go from aqueous to solid, and the solid one is going to go from solid to aqueous. And you can remember this by just looking on here. So we were given an iron that is aqueous, so that is right here on the right side. Therefore, it's going to go the other way to the solid. So this one is going to go to iron solid. Fe solid. So now this equation isn't balanced. So if we want to balance it, this is where we have to do the half reactions. Now, would you like to do an example with the half reactions, like how you would balance it?
Sure.
Okay. Now we'll do one on Monday too. I know these are kind of involved, but
I'm just trying to get the chem homework done.
Yeah, I didn't realize it was done due this week. Otherwise, I would have tried to prioritize this. This is really hard to fit chapter 4 in 1 week. I'm surprised they're doing it. So let's do the oxidation and reduction reactions. Well, which one of these, silver or chromium, which is oxidized and which is reduced?
Well, they'd both be 0, right?
So chromium to start would be 0, but this one is explicitly stated as +1. Yeah.
So it's so Ag is oxidizing, right?
Ag is doing the oxidation. Chromium would be the one that's being oxidized. So chromium is going from 0 to +3. In other words, it's losing electrons. So we say chromium goes to +3. Now, what else do we put here? There's something else we put here. Anyone know what it is?
The electrons that are gained or lost.
Yes, and where would you find that?
The table.
Right, so we run over to the activity series and see where's chromium. Here's chromium. This goes to 3 plus 3 electrons. So this is the plus 3 electrons. What about the other one, which is the reduction half? So when we say half reactions, we mean like we're breaking down this whole reaction into the part that is being oxidized and the part that's being reduced. So the reduction half would be then the silver. So Ag plus aqueous goes to
back, right?
Yes, this one is going to be going backwards. So Ag solid. Now again, we're missing something in this reaction, and that is going to be the electrons. So let's go to the activity series and find silver. Silver is down here. So this one is Ag solid, goes to Ag plus and 1 electron. So this is going to have 1 electron. This is E minus.
Does it matter how you write that? So I put Ag plus Aq yields to 1 electron plus.
So there's a notation standard, and that is you should always have the electrons as like you're adding them. So technically you could write like minus electron over here and erase this. You technically could write this. You just have to have the, or wait, no, it's plus electron, isn't it?
Yeah.
Plus electron. No, wait, it is minus, isn't it? Or it is minus. Electron. But I guess you always want to have it just like what's on the activity series. So I guess that would be what I would say. So just go to the activity series and you'll say you have a plus E minus on the aqueous side. I guess that would be the only advice I can say is stick to whatever is right here.
Could you
So
just like look at it and see that?
Yes. Yep. So Ryan said, could you just look at it? Yes, of course. That is what this table just kind of helps you get to being able to do it visually. So if it's easier for you to just say, well, look, chromium's going to plus 3, therefore there has to be 3 electrons, just do that. Yep. Okay, now the overall balanced reaction. So the overall balance reaction. So what we're doing here is when we balance reactions, remember, we need to balance the number of atoms on both sides, but we also need to balance the number of electrons. That's why we're doing these half reactions. Because just like we can't create or destroy atoms, we can't create or destroy electrons. Now, the way you do this is you want to match up the number of electrons in this equation and the number of electrons in this equation. Now, the first one has 3, and this one has 1. So what should we do to the second equation? So this one, we're going to want to times this reaction, everything by 3. So everything in this reaction, we want to times it by 3, because that would yield a same amount of electrons on the left side of the arrows, or on the reactants, as the same amount of electrons on the products. Now let's write down the overall what we have. So we have chromium solid. I'm just taking what we have above, plus we have silver, but we're going to have 3 silvers, aqueous, and we're going to now have 3 electrons, and this is going to go to, so I just took all of this stuff on the reactant side, and this is going to go to chromium 3 plus, aqueous. This should be aqueous here, shouldn't it? plus 3 electrons. And then we're going to have our 3 silvers plus 3 AGs. Did you guys follow up until this point? Okay. Now the last part is to cancel anything that's the same on both sides. Now look, we have 3 electrons here and 3 electrons here. So I'm going to cross those off, and whatever's left is going to be our balanced chemical reaction. So in this case, what we are told is for every chromium we want to react, we actually need 3 silvers to perform that reaction. What questions do you guys have on this?
You wouldn't cross out the AGs because one's a solid and one's aqueous, right?
Correct.
Okay. I think I'm good then. Thank you.
Cool. Yeah, we'll try to do another one of these on Monday. But if you guys have any other questions, feel free to stick around for another minute. Otherwise, we'll see you guys on Monday.
So then would your chromium be